Hello and welcome back to Introduction to General Relativity. In the previous lecture we introduced tensors, which are a way to capture multi-dimensional information on manifolds. These tensors belong to a vector space constructed by the tensor product. In the previous lecture we only considered the basic vector space construction of the tensor product, and we essentially completely ignored the structure of the underlying manifold. In other words, we applied the tensor product to the vector space Vp at a point in the manifold. The purpose of today's lecture is to study the consequences of the extra data provided to us by the manifold. Namely, we have not just one vector space, but a field of vector spaces, one at each point on the manifold. And under maps of the manifold, various aspects of these vector spaces change. That's the purpose of today's lecture, to understand how do things change under changes of coordinates of the manifold. So how do vectors, dual vectors, tensors, how do they behave under mappings of the manifold in question? So to commence this discussion, we'll start by recalling the definitions, or rather the notations, the operations we've considered in the previous lecture, and apply them more directly to the general case of the vector space Vp in a manifold. So let P be a point in a manifold Vp the tangent space at the point. Let's now study the behavior of Vp, or elements V in Vp, elements V star in Vp star, etc. under changes of coordinates on the main manifold. So let's take a look at Vp star. So namely, Vp star is the dual of the tangent space Vp. Vp star has a name. When you take the dual of the tangent space, you give the resulting vector space Vp star a name. You call it the cotangent space in differential geometry. And the elements of Vp star are now called covariant vectors. Given a basis, we have a basis for Vp. This is the standard coordinate basis that we've been considering in the previous lectures. We formally define a dual basis, E mu, and we employ a very suggestive notation, although at this point you should be cautioned against interpreting this notation too literally. This is just a symbol. Symbol so far. Later it'll acquire an interpretation of an integration measure, but for now we define this dual basis. Well, how do you define the dual basis? Well, with a Kronecker delta, right? If you have a basis, then you get a basis for the dual vector space just by introducing the relations, the dual vector basis E mu, according to the fact that when you apply E mu to an element of Vp, you better get a basis vector of Vp, you better get 1 if they're the corresponding basis elements. But if you apply the notation here, then you get this very peculiar looking relation here, namely that dx mu, interpreted as a linear function on tangent vectors, has to obey this Kronecker delta equivalence relation. Now again, I want to stress dx mu is a notation, nothing more at this point. It's a highly suggestive notation, but don't look to interpret it any further. Dx mu is a symbol for a linear function on the is a symbol, it's a linear function of tangent vectors defined by star. Nothing more, nothing less. It's just a symbol so far. Probably the most confusing part about differential geometry and general relativity is that the notation is so highly suggestive, and it asks you, or you are very motivated to try and interpret these symbols further, put more meaning into them than what's handed to you in the definition. That's not the case. Dx mu is just a linear function of tangent vectors, nothing more, nothing less. It's nothing to do with derivatives and so integration measures or anything yet. Now, what happens under a change of basis? Now, change of basis is perhaps a poor choice of words at this point, because we have a vector space VP and we have a basis for VP, and we can change that vector space. But what we should say is change of coordinate system. If you change your coordinate system of your manifold, you get a different basis for VP. We know how this basis behaves under a change of coordinate system. So we know that a vector with components v mu in the original coordinate system has components v mu prime in the new coordinate systems according to this Jacobian rule. And that was the this is the so-called vector transformation law. We derived this change of basis formula when we introduced tangent vectors. So if we change a coordinate system, a coordinate system is extra data handed to you by a manifold, and it provides you with a basis for your vector space VP. If you change your coordinate system, you change your basis for the vector space VP, and therefore a vector in one basis looks different in the new basis. And how does it look different? Well, via this Jacobian factor here. So how does the components of a covector or covariant vector look like in a new, with respect to this new choice of basis? So here we go. Let omega be a covariant vector. Well, because we have already a basis for the vector space VP induced by these dx mu's, we can always write omega as a linear combination of these basis vectors. Now, how does that omega look like in terms of the basis vectors induced by the change of coordinate chart? So we want to understand how to calculate omega prime mu primes. How does that look? Well, the way to do it is to construct a basis independent quantity that you can then study to infer the behavior of basis dependent things. So apply omega to V. So omega is nothing more than a linear function of tangent vectors. V is a tangent vector. And if you apply omega to V, you get a number. Right? That's the definition of tangent vector, of dual of a vector. That if you apply a linear function to a vector, you get a real number. So we know that omega v is just a number, doesn't depend on the basis. But now let's expand our tangent vector in terms of our coordinate basis that comes from this chart that we've decided to focus on. And well, omega is a linear function, so I can push it past the summation symbol here. And remember, these funny d, dx mu's, p's are just formal elements of a vector space. Now omega eats vectors and produces numbers, and what number does it produce? Well, it produces omega mu, the components in the original vector space. But this is also equal, exactly the same quantity as if we'd computed the vector in a new chart, right? And we use the vector transformation law to write this vector in the new coordinate system in terms of the old. So we get a Jacobian factor. So we can also equivalently write the vector here as this linear combination of basis vectors. Oops, there's indeed a prime missing here. And so then we can use the fact that omega is a linear functional of vectors and so on to infer that omega prime mu prime contracted with v mu via this Jacobian factor is exactly equal to omega mu contracted with v mu. Now, do you see here I'm starting to get careless with the summations. So let's go and put the summations in, but sooner or later I just expect you to be able to interpret these expressions as written, putting in the summation symbols as required. So on the left here I've got a repeated mu index, so that really means in the Einstein summation notation sum over mu. Here I've got a repeated mu index and a repeated mu prime index, so I have two summations that are required here. So we learn that the components of the dual vector omega with respect to the new basis can be obtained by this inverting this Jacobian matrix here. Right, so we got that omega mu, so this is true for all v mu here. So we have that omega mu is equal to the sum, I'm not even going to do the summations anymore. Right, so we know that omega mu, the components in the old basis, are related to the components in the new basis via this Jacobian factor, but we want to invert this expression, and we can, right, because the Jacobian is invertible matrix. So we learned that the components of the dual vector with respect to the new basis are dx mu, dx prime mu prime, so the inverse of these Jacobian factors. So that's how the components of a dual vector look like in a new coordinate basis. They're related by the change of variables formula in this fashion here. So in general, for a tensor T of type KL, we can work out via an equivalent or analogous argument how the components change when we change the coordinate basis. So I'm going to employ the following notation to refer to this the components of this tensor. So the underline here indicates mu1 all the way up to mu k. The underline here indicates, the same, but the underline here indicates mu1 all the way up to mu l. And the sum here is over all the indices. So if we choose, and v mu is a basis, which basis is it? Well, it's d, very tediously, d dx mu1 at p tensor d dx mu2 at p dot 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 d dx mu k at p, and then we've got v nu dual basis has got to be dx nu1 at p, d dx nu2 at p, and you can drop the at p because it's understood from now on. And so applying these two rules that we have, the vector transformation law, which is up here. So the vector transformation law tells us how the components of a vector change when you change the coordinate chart, or coordinate system. And the covariant vector transformation law here tells us how the components of a covariant vector transformation transform under change of basis. You can actually just put these two expressions together and then apply a similar argument, apply t to smooth vector and covector fields, and then you learn that the components of a tensor under a change of coordinates behave as follows. So the components of t in a new coordinate system are given by the so-called tensor transformation law. So t prime, mu 1 prime, all the way up to mu k prime, mu 1 prime, all the way up to mu l prime, are given by a sum over mu 1 to mu k, mu 1 up to mu l. So they're given in terms of the old components, multiplied by these Jacobian type factors here. Okay, so that's you can quickly convince yourself of this by applying the tensor to various, contracting the tensor with smooth basis vector fields of simple tensors. And here and when you do, you infer that the components of a tensor in one coordinate system have to look like this in the new coordinate system. So that's the so-called tensor transformation law. Which I'm going to label star, I think. Now, here we come to this sort of terminological overlaps that inevitably happen when you have fields using similar things, similar quantities. We're going to call a collection, so a collection of numbers t mu underline nu underline, depending on position p in a manifold, that transform like star is what is classically referred to as a tensor, what I'll call a tensor field. So that's something that classically you'll hear people saying this thing is a tensor, this thing is not a tensor, and they'll have in mind a manifold, and they'll have in mind a collection of numbers transforming according to star. Now, I want to stress here two things. The first thing is that what we call a tensor depends on whether or not we have the data of a manifold there. So I call by a tensor any element of a tensor product of vector spaces. Forget the manifolds, there are no manifolds. And a collection of numbers that associated to a manifold that when you change coordinates transform according to this transformation law star, that's what I'll call a tensor field. Well, at least I'll try and do that. I might forget to do that. So that's a very important definition. So another point that I want to stress, the second point, is that you can have collections of numbers defined on manifolds that don't transform like star. Just because you write them, just because you have a collection of numbers doesn't mean they transform like star when you change coordinate systems. So those are non-examples of tensor fields. They're not bad. It can happen and will happen that we will have collections of numbers that we associate to points in a manifold, but they just don't transform like that. That's the generic situation. So tensor fields are quite special. Vector fields are a subcase of tensor fields. And covariant fields are also a subset. Now, here's an important notion that we can apply immediately to tensor fields. I haven't said anything about how smooth the tensor field is. Right? It might not even be differentiable. It could transform that way, but not be differentiable. Let's sort that out. So a smooth tensor field of type KL is one for which the following scalar function is smooth. So for all smooth omega 1 through omega k and smooth v1 through vl. I noticed that I haven't told you what it means to have a smooth covariant covector, dual vector. So if you have a dual vector field of dual vectors, then that is smooth if for all smooth v, omega v is C infinity. Okay, this is how we can assess the smoothness of a tensor field. Remember, a tensor you can always interpret in two ways: as an element of a tensor product vector space, or as a multilinear map of the dual of those vector spaces. Here we're thinking of this tensor field as a dual, as a multilinear map. As it's a multilinear map, we can insert in the arguments k covectors, covariant vectors, L L normal tangent vectors, and that's a number now, and we can assess how smooth this function is by we can easily assess how smooth a number is, a function on a smooth manifold, and we therefore define a tensor field to be smooth if this number t omega blah 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 is smooth for all smooth arguments. Now, this is highly abstract. In the past couple of lectures, I've built up this very abstract formalism to talk about very general collections of multilinear objects associated to manifolds. Why did we bother with all of this? Well, the answer is, of course, we're actually going to need it when we describe various quantities, physical quantities associated to manifolds. But even before that, I would argue that we need this formalism to talk about the various quantities that can appear in physics. And now I'm just going to give you, for the rest of the lecture, I'm going to list a bunch of examples, the most important examples in physics of tensors, and vectors and tensors. And this will serve as a motivation for the previous couple of lectures where we've built up all this formalism. Now we're going to exploit the formalism to label various quantities that you've probably seen before. So the rest of this lecture is now going to be concerned with examples. And it's going to be very helpful to take all these quantities that you probably are very familiar with and start reinterpreting them as tensor fields or vector fields on manifolds. So the first example is presented by currents and densities in special relativity. So what manifold, if you're talking about tensors, vector fields and so on, you should name the manifold at the beginning. So the manifold we have is R13. It's not yet, the distinction between time and space is not yet important. We're just thinking of that as the manifold R4. But it will become presently important when we think about various diffeomorphisms of this manifold. So I will delete that identification because it actually will become important in this example. So imagine we just got flat Minkowski spacetime. Here's my cartoon of flat Minkowski spacetime. There's the light cone here associated to an event at the origin. and we've got space and time. So this is the manifold that plays a major role in special relativity. And suppose we have a system of n particles moving in this space-time. Okay, that was a bad particle. Here, we don't want anything moving faster than the speed of light. So here's a bunch of particles, and each particle has a position xjt at a certain time, and it has a charge, so they're charged particles, well, potentially charged particles, qj. So we have n particles and we're going to label them 1 through to capital N. So we have these particles, and they're moving around in space-time, and we want to assess like how many of them are in a certain place, a location in space-time, and where are they going. So when you have a bunch of charged particles and you want to assess where they are and where they're going, then you can form the density and current. You can construct the density and current. So let's talk about the density, and in particular the density of charge here. We could equally as well have think of the charge as their mass. Right? So just charge, so we're looking at the density of this quantity that we're calling qj. So the density for this distribution of particles is a function, right? The density is 0 if there's no particles there, and a delta function if there is a particle there. So the density is a very simple simple function, and here it is. Right? So the density of charge of these n particles is given by a bunch of delta functions. So these are Dirac delta functions. Go Google it if you don't know what they are. I believe you do know what they are. One of the prerequisites of this course is that you know calculus, linear algebra, and basic physics, and the Dirac delta function is covered in multiple ways during the first year of most physics degrees. So the density of charge throughout space at a given time slice throughout space, the density of charge is a bunch of delta functions. So there's no charge where there's no particle, and there's a infinite charge where the point particle is. But of course, when you integrate over all of space-time, or over all of space, that'll give you the total charge. It'll give you a finite number. Now, where are these particles going, or where is the charge going? To answer that question, we introduce the current, which is a 3 vector. And this current is also a sum of delta functions. So it's given by the following expression, where now we also include the velocity of these particles. So we multiply the charge by the velocity and multiply that by a Dirac delta function where the particle is, and that gives us the instantaneous velocity vector of this charge, or the instantaneous current vector of this point particle with charge qj. Now this is sort of done in a mishmash of 3 vectors and 4 vectors. We can define a 4 vector and hence this 4 vector will have a chance of being a tangent, an element of a tangent space. So we can define a 4 vector j mu by setting j mu is this following vector here. You put the density up the top, right, in the time-like component, and then you just put the rest of the current vector underneath it. So now you've got an exercise. You've got to synthesize the information you've received about defining tangent spaces and what you know about special relativity. So it's a slightly non-trivial exercise, and that is you've got to argue that j mu is a vector, in VP. It's a vector, not a covariant vector, under changes of coordinates. So it's a vector field Under changes of coordinates, what changes of coordinates are appropriate for Minkowski spacetime? Well, Lorentz transformations. They are the diffeomorphisms of the Minkowski manifolds. Lorentz transformations are the ones. Are the changes of coordinates that are allowed in special relativity. So you know all about special relativity. That was one of the prerequisites of this course. So you know exactly how to interpret this expression here. So when you make changes of coordinates according to a Lorentz transformation, you can study how this vector J mu transforms. And you know how it should transform if it's to be interpreted as a vector field. It should transform exactly like this equation here, the vector transformation law. So you've got to check that that's actually the case for this quantity called the current, or the 4 current in this case. This 4 vector J mu. That's your job. That's the first job for you right now. I highly advise that you pause the video to do that calculation. It's a little bit non-trivial, I must admit, because you've got the expression here makes reference to time, and so that gets transformed. So you have to be a little bit creative about this argument. All right, energy momentum tensor. So this is something that plays an extraordinarily important role in general relativity, but is often sort of not particularly well described in special relativity textbooks, and often even in general relativity textbooks it can be a little bit mystifying how they introduce the stress energy or energy momentum tensor. Now I'm going to deviate from the textbook of Wald to give you what I think is a far more transparent definition of the energy momentum tensor. So again, we're going to work with this nice simple manifold of Minkowski spacetime. We're going to consider our collection of n particles moving in Minkowski spacetime. And they're moving, so there must be some associated energy momentum 4 vectors for each particle. So each particle has an energy momentum 4 vector at a given time and its location. So I'll just write it like this, with energy momentum 4 vectors pj mu, and here we've got n of them, so j is running from 1 to n. So what we're going to do is we've got to each particle, instead of just say their charge now, we've got a distribution of 4 momentum for each particle, and I'm going to build a bunch of numbers that capture the distribution of the 0th component of their 4 momentum, the 1st component of their 4 momentum, and so on. So, but let's start at the beginning. So the density of their muth component so the density of the muth component of 4 momentum is we're going to give it a name. It's going to be this function here, t mu naught x comma t. And we can simply ask how much mu component momentum is there at a given point in space-time? Well, the answer is either 0, because there may be no particles there, or if there is a particle there, then the distribution is highly concentrated where the particle actually is, with a delta function. So this quantity here, t mu naught, is a distribution function. It tells us how much mu component of 4 momentum there is in a given point in space-time. So most of the time it's 0, but if you happen to land on a particle, it's highly concentrated in infinitesimally small space with a direct delta function, and that's where all that form momentum is. So this is a density, right? It just tells you where stuff is. Now we can also, corresponding to any density, just as before, we can introduce the corresponding current, right? That tells us where it's going. So the corresponding current, I'll use this notation to capture it, is just the velocity multiplied by the density multiplied by where it is. So we got pj mu t, that's the muth component of form momentum. Now, where's it going? Well, you got to work out where's it going is given by the velocity. So that's dx mu, dx dt. And since we're looking at the kth element of this current, we need to have a second index. So we can combine this to a single formula. So just before I do that though, just take a look at this thing here. This current here is just, this is the analog of J, the kth component of this J in the previous example. And this T naught mu is the analog of J, of epsilon, right, the density. Now, in the previous example, we were just looking at the distribution of charge throughout space-time and how charge was moving around the current. In this next example, we've got four quantities that we want to assess throughout space-time. We have the zeroth component of the energy momentum forward vector, like the energy. So how is energy distributed throughout space-time and where is it going? So for that, we need it gets its own current vector, which we call T naught naught and T naught K. Then we have the first component of momentum. How is that distributed throughout space-time and where is it going? For that, we need T1 K and T1 naught and so on. So we end up with 16 numbers actually to assess where all the form momentum in space-time is for these n particles and where it's going. So we can, and it turns out we can combine this to a single formula. That's why I suggestively wrote it as I did. Now x here, I've got this lowercase x without the underline anymore. This is going to happen a lot. That I'll do this. X stands for x. X is a 4 vector which stands for the x spatial components and the t component. So we can combine these two quantities, into a single formula, and what do we get? Well, this thing here. So this is the distribution of the muth component of form momentum and the nth component of the current, where it's going. So here, like just a reminder, right? X naught at t is none other than t, right? Because the zeroth component of a space-time location 4 vector is just the time. And now since, if you look at the energy momentum 4 vector, since you know that that's equal to the energy of the particle multiplied by the derivative with respect to t of the position, we have a nice representation for this field of 16 numbers that makes explicit that it's symmetric. Okay, so now we have this way of representing these 16 numbers that are defined at every point in space-time manifold. We have a way of representing them so it's absolutely clear it's symmetric. So T is symmetric. And what does that mean? Well, i.e. that T mu nu equals T nu mu. So now we've got this field of numbers. So we ask, is this a tensor field? it's absolutely, I'd claim it's not very obvious at all that this thing here is a tensor field, right? It's a collection. I hope you agree that T mu nu x is a collection of numbers that we can associate to every point in Minkowski spacetime. So here's Minkowski spacetime. Here's the light cone. Here are the n particles. I'll just draw two. Oops. Here's a particle, here's a particle. And now at every point in space-time, x, we have T mu nu x. Now it's a collection of 16 numbers. Now at this point that I've just chosen there, that's equal to 0. T mu nu x is absolutely equal to 0 at that point in space-time. There are no particles at that event in space-time. However, just here, if I had chosen x prime, T mu nu at x prime, well, that's now equal to infinity, right? Because there's a delta function there. And so it's T mu nu doesn't look very much like a nice tensor here. The problem is that we've got these idealized point particles. Each particle is considered to be an infinitesimally small point. What we really should do is smear these particles out, and then T would turn into a much nicer field. Nonetheless, I'm convinced you can work with delta functions. You know how to work with delta functions by now. So we've got this collection of numbers. I claim that you can draw the trajectories, the 4 trajectories of all these particles in spacetime. Then you can, to every point in spacetime, you have this list of 16 numbers, T mu nu x. And most of the time it's 0, and where you hit a particle, it's a delta function. And the question is this a tensor? Like, I would say it's absolutely non-obvious from this expression here that that's a tensor. There's no way you should, I don't believe by looking at that expression you should instantly know that that's a tensor. That takes a little bit of thinking to prove. So I'll give you a couple of hints on how to convince yourself that this actually is a tensor. So if you write T mu nu x as an integral over the proper time, so this is a big hint, and so far we have a threefold Dirac delta function, but now I've introduced a fourth Dirac delta function, so now we've got 4 dimensions in the story. Then now, if you look at that expression on the right-hand side here for T mu nu, everything starts to look covariant now, or covariant enough, so that you can argue that under diffeomorphisms, and the diffeomorphisms that we care about in special relativity are Lorentz transformations, x prime nu is x nu mu x mu. That's the coordinate transformations that matter in special relativity. That the components of this tensor, and it is a tensor, right? I wouldn't have started this whole discussion if it wasn't a tensor. So that the components T mu nu in the new coordinate system are given by the components in the old coordinate system according to this rule here. But this is none other than the tensor transformation law, right? Note that lambda mu prime mu is just dx prime mu prime dx d mu. So it's a tensor of type 2, 0. This is a really important tensor. It plays an extraordinarily important role in general relativity. This is how we assess the stress energy content of spacetime. We will assess it with this function T mu nu. So do spend some time to think about these exercises that are given you and work on the exercises to get some facility with this tensor. And then, because we're going to use it a lot. Okay, and now I'm going to introduce to you the other main player of general relativity, the one that assesses the actual curvature of spacetime, effectively, implicitly. So our third most extraordinary example of a tensor is one that characterizes the geometry of a manifold. It's called the metric tensor. So what is a metric tensor? So a metric tensor, G, is a tensor of type 0, 2. So what does that mean? Well, it eats two vectors and gives us a number. And it's not just any tensor of type 0, 2, it's symmetric and non-degenerate. So what does symmetric mean? Well, symmetric means that if you give it two vectors, then and you substitute them into the two arguments, that you get the same number as if you put the vectors in the reverse order in the arguments of G. And non-degenerate means that the only way that GV, V1 equals 0 for all V and Vp is if V1 itself is 0. So this set of numbers here, this is a tensor of type 0, 2. It's got some additional conditions on it, namely that it's symmetric and non-degenerate. Whenever you have such a thing, a field of tensors like that, then you call it a metric tensor. So I said tensor, but I should say tensor field. There's one of these at every point on your manifold. And why do we bother with this funny thing? Well, it's exactly the data you need to supply us with a notion of length on a manifold. We don't actually have yet a notion of length on a manifold. But that requires a little bit more information than just the information of a manifold. Actually, first of all, it just supplies us with the notion of infinitesimal length. Actually, later we get a notion of length by the introduction of things called geodesics, but we're not going to do that just yet. And the reasoning is as follows. You can think of an infinitesimal displacement as being represented by a tangent vector. You know, a tangent vector tells you how to move along a curve just by a teeny infinitesimal bit. So that's like a displacement. And given a tangent vector, then given this identification here, a tangent vector is like a little displacement along a curve on a manifold, then an infinitesimal squared distance should be somehow a quadratic function of a tangent vector. Is a quadratic function of tangent vector. And how do we get this quadratic function from this tensor, this metric tensor? Well, okay, I'll show you how. So choose a coordinate basis. Expand G. G is a tensor of type 0, 2. So when you expand it with respect to a coordinate basis, we've got to use the dual basis. Dx mu, dx nu. This is sometimes also called ds squared. G is also called ds squared. Now we often omit the tensor sign. And this is highly confusing, I think. You know, we go to all this trouble of introducing all this notation and then we start throwing it away indiscriminately. But that's it, it's notation. You can't fight notation. If people use it, you've got to be able to translate it. So people often horribly confusingly drop that tensor symbol and write ds squared equals the sum over mu nu g mu nu dx mu dx nu. And why does that work? Well, it works in this particular case because the tensor is symmetric. And so there's no ambiguity in dropping that tensor sign. If the tensor were not symmetric, there would be an ambiguity and you wouldn't be allowed to drop that tensor sign. So what you're going to see me do, of course, is the worst of both worlds. I'm going to have expressions with and without that tensor sign, and you'll just have to get used to it. Because you will anyway, because every textbook does this. And if you don't get facility with changings of notation, then life will be very difficult for you. Now, we've got this symmetric collection of numbers now associated to every point, and I'm going to argue to you now that we get an infinitesimal square distance from it as follows. So a metric, what does it do? Well, it actually gives us, you know, you could talk about infinitesimal square distances and so on, but let's just say plainly what it does give you. A metric actually supplies us with the extra data, exactly the extra data, no more, no less, of an inner product on Vp for all p in the manifold. So if you want to compute the inner product of two vectors in a real vector space, you need more data, right? You don't, that's not canonically given in the definition of a vector space. So you need this extra data. Got to get it from somewhere, and that extra data is a matrix, a symmetric, non-degenerate matrix of numbers. I'm not saying it's not necessarily positive definite in this course. That's a warning. And how do we actually define this inner product? Well, take this coordinate form in terms of these dx's are dual vectors, and then apply them to a vector. And in other words, contract this tensor. So dx mu can eat the v, dx nu eats the w. It doesn't matter if the v and the w's are in the opposite order because g is symmetric. So this is unambiguous. And we get that this way, the following expression for the inner product of v and w, where of course v mu, where v is the sum of v mu d dx mu at p in terms of the coordinate basis, right? Similarly for w. So we have what does a metric, a tensor of type 02 that's symmetric and non-degenerate supply us with? It supplies us with an inner product at every point on the manifold. Every point in the manifold has an inner product now. That's exactly the data that it gives you. Now the Gram-Schmidt process can be applied to any inner product, any real inner product vector space. At this moment, we can now apply Gram-Schmidt. To produce, what does it produce? It produces an orthonormal basis. This is a much more special basis than the ones we've been considering so far. And what does orthonormal mean? Well, it means when you evaluate the matrix, when you insert these basis vectors into this tensor of type 02, or evaluate their inner product, right? You should get the Kronecker delta function. But not quite. Slow down, right? There's something else that you get. You get, you diagonalize G. Now, most of the time when you've done Graham-Schmidt before, you've been applying Graham-Schmidt to positive definite symmetric non-degenerate matrices, and you've never had to worry about this extra factor that can appear. But this extra factor can appear, this S mu factor, for non-positive definite inner products. So the number, it turns out the number of positive and negative signs of this of these numbers here is actually an invariant. It's independent of the orthogonal basis that you end up with the Graham-Schmidt procedure. And it has a name, it's called the signature of the metric G. So a metric with S mu equals +1 for all mu, such a metric is positive definite and is given a special name in differential geometry. It's called Riemannian. G is positive definite. It turns out that in the spacetime that we live in, the metric that we associate with our geometry in the spacetime we live in does not have a signature of all +1s. In fact, the metric of our spacetime, or of spacetime, has signature -1, +1, +1, +1. So the timelike component has a -1 when you do the Graham-Schmidt procedure to the metric, and all the other ones, spatial components, have a +1. Okay, there's one final comment I want to make about metrics, an extremely important comment that will influence our interpretation of dual vectors and tangent vectors. So a metric G is, well, we've learned in the previous lecture, of course, that tensors of type 1, 1 can be interpreted in 3 ways. Well, a metric is a tensor of type 0, 2. It can also be interpreted in a multitude of ways. So a metric G is can be simultaneously interpreted as a 0, 2 tensor, and also as a vector in a tensor product vector space, and also as a multilinear map from VP cross VP to R. And it's also as a linear map from, now in the previous lecture I gave an example of how a tensor of type 1, 1 gives you a linear map from V to V. But now we've got a tensor of type 0, 2, and this gives us something very interesting indeed. It gives us an interpretation of G as a linear map from VP to VP star. And how do you get that linear map? Well, you contract V, the outer product of V and G, according to this recipe here. You stick V in the second argument of the metric, And now you get handed a function that goes from, so stick v in the second argument of g. What is this thing? Well, g naturally eats vectors for breakfast and gives you numbers. So where g, you can put a vector into the first argument of g with a v in the second argument, and that's a natural way for g to eat vectors for breakfast and give you a number. So g dot v is got to be an element of the dual space, vp star. Now, this map is one-to-one and onto, and it gives something very special. It gives us a canonical, a standard, basis independent way correspondence or identification between the tangent vector space and the cotangent vector space, or vectors and dual vectors, right? So this correspondence here, where we're handed g. So g is a metric. It's given to us. Let's assume that someone's handed it to us. Then given g, we can take a tangent vector v, stick it in the second argument of g, and then we get a linear functional. So we'll call that linear functional omega. And that correspondence, where you associate to every vector a corresponding linear functional omega that's now a cotangent vector, that's basis independent. I never wrote a basis down in this equation here in the box. And so that's now a basis independent correspondence between vectors and dual vectors. It's an extremely powerful tool, and it's one that is once you have this extra data of the metric, is absolutely determined, and it's so useful that many authors don't even introduce cotangent vectors at all. They just immediately from the outset assume that they have the metric, the extra data of a metric, and they identify from the outset all cotangent vectors with vectors via this map in the box. So that's I find that a bit confusing, and also it's much more. It makes much more sense, in my opinion, to not rely on the extra data if it might not be there for some reason in your studies. And so the extra data of a metric may very well not be present in all your considerations of manifolds. So it's far more important to understand how these things come about and not think that these magical miracles are actually general results. So the final topic for today's lecture is a notation. It's a very helpful notation that we're going to use throughout our description of the rest of differential geometry we need for general relativity, and probably for just about everything in the rest of this course. And it's called abstract index notation. So suppose you have a tensor of type KL. There it is, T. We have a tensor of type KL. So we can think of T as a multilinear map. From, of course, VP many times tensor I think I made mistake there. You can think of a T, a tensor of type KL, as a multilinear map that eats K dual vectors and L tangent vectors and produces a number. Now you can specify T via its components in a basis. I mean, there's no way around it. At some point, if you're going to do some kind of calculation with physics, you're going to need to specify this thing somehow, and you're going to need a basis. Let no one tell you otherwise. There's no such thing as doing physics without basis at all. But there is such a thing as doing as much of physics as you can without a basis. So we can specify T via its components in a given basis. Choose your coordinate system, measure, do some experiments, and then measure your densities and so on with respect to that basis. Then you can specify this tensor. However, for many manipulations, especially ones where you want to get a basis independent answer, you don't really need the actual components. You can do many manipulations without referring to components. In fact, often it is enough just to know which arguments of T are take vectors or dual vectors. And we can capture just this information by labeling each argument with a symbol, by naming. By labeling each argument with, and we'll try and be consistent throughout the course, with a lowercase Latin letter. So what we're going to do is we're going to label upper index, so superscript, superscript indices, label code contravariant, entries, and lower index subscript, not lower. Label covariant entries. An example is much more powerful than a general discussion. So what we're going to do is, for example, we use lowercase letters to label which arguments, which entries correspond to which types of arguments. So this thing here labels a tensor, or denotes a 2-2 tensor. So here the letters denote arguments, or label the arguments and their type, not the components of the tensor itself. So lowercase Latin letters denote, or rather label, arguments and their type, and not components with respect to a basis. And this notation can be very helpful, as we'll see in the future lecture, for doing computations without having to explicitly introduce a basis. So we won't go into this notation any further today. I'll just have the notation introduced. In the following lecture, we'll take a slightly more detailed look at this abstract index notation, and we'll introduce some subspaces of tensors that will be very helpful when discussing certain quantities in differential geometry. And then after that, we can jump into the topic of curvature of manifolds. But that's it for this week. Thank you very much, and goodbye.